Hi everybody, today we're going to look at Galileo's kinematics equations and see how they're related to each other. I'm going to do that by deriving a couple of them. Okay, first of all, let's take a look at average velocity. Okay, average velocity is equal to v1 plus v2 over 2 if the acceleration is constant. And that's always something we have to consider. Galileo's equations will only work for constant acceleration. It's also known as uniform acceleration. Where does this come from? Well, if we remember the graph of the velocity time graph, the slope of a velocity time graph gives us acceleration. And if the velocity time graph is a nice straight line like that, that means the acceleration is constant. And that fulfills the requirements for Galileo's equations. If we take, like say, a v1 here and a v2 here, we can find the midpoint of those two because of this fact that this is a straight line. We can find the midpoint of the section between here and here, extend that over, and that gives us the average velocity. So that's where this relationship comes from right here. v1 plus v2 over 2, average velocity. Okay? So we can call that equation 1. Alright? Another important relationship is the idea of the definition of acceleration. Acceleration is defined as a change in velocity per change in time. Okay? And we can also write it like this. A equals v2 minus v1 over t. I just didn't put the delta there. That's just a shorthand. Okay? So that's an important definition. That's the definition of acceleration. Let me move this over a little bit. Okay? That's the definition of acceleration. Now we can rearrange that to get a different version of that and solve for v2. And if take that, and v2 would be equal to v1 plus at. Okay? So that's usually the way you'd find that second equation in textbooks and such. Okay, we also remember from elementary school that distance is equal to rate times time. And that's the old classic freight train problem. It's going 50 miles per hour times 10 hours. The distance traveled is 500 miles. But that only works if we're putting our rate being the average velocity there times the time. So distance, rate times time, that's a good formula right there. Average velocity assumes, in this case, that this motion is still constant acceleration. Okay, it still has constant acceleration. Okay, now we have some other relationships too. For example, if we combine equation 1 with equation 3 here, okay, we see something interesting happen. So let's do that. So we'll combine 1 and 3. So we'll get V average times T. We'll substitute for V average. We'll put in v1 plus v2 over 2 there. So we end up with, for average velocity, times t. Okay, and that's pretty useful right there. I'll pull out the 1/2. So far so good? Okay. So that's a useful relationship right there. And we can then do some other things with that, which I'll have to put on hold for later. Now all we have to do is see if we can combine, let's say for example, equation, this equation here, V2 equals V1 plus AT, and substitute that in for V2 right here, and see what we get. So what does that give us? Well, let's see here. So instead of putting the letters V2 here, I will substitute in this V1 plus AT. And then we're going to multiply it by T. If we simplify that, a half V1 plus a half V1 is a whole V1 times T plus 1/2 AT squared. And that, my friends, is another famous kinematics equation brought to you by Galileo. We can call that equation 4. Okay? Last but not least, if we take equation 2, which is basically the definition of acceleration, and solve for t, we can get t equals v2 minus v1 over a. That's simply from equation 2 rearranged, and we can substitute that in for t right here. Okay, and so what do we get? We get delta x equals 1/2 v1 plus v2. And so instead of t, now, I guess it'd be easiest to sub it in there. Instead of putting t there, what we'll put is the equivalent of t, which is v2 minus v1 over a. Okay, now if we simplify that, we get delta x equals v2 squared minus v1 squared over 2a. And then we get our final equation from that. If I better shift this up though first, huh? So we get delta x equals this, and then our final equation would be, if I rearrange it in familiar form and that you'd find in textbooks, v2 squared minus v1 squared equals 2 times acceleration times delta x. There is the fifth and final kinematics equation. So now you can see how the different relationships among these equations. And since they are so interrelated, that might give you a feeling for, hey, maybe one student might want to use these two equations to solve a problem, and another student might use a couple of the other Galilean equations to solve the same problem. It gives you flexibility